Okay, good evening everyone. My name's Troy. I'm a postdoc at Kyushu University. So my talk's about how magnets work. So hopefully I'm going to try and explain how magnets work and some of the technology we use magnets for. So this is from the Insane Clown Posse song, and the line is something like, "I don't need no scientist, but we actually do need scientists to tell us how these things work." Okay, so this is a bunch of things where magnets are involved. We've got headphones, hard drives, motors. The Earth is a magnet as well. So hopefully by the end of this talk, we'll be able to understand how some of these things actually work. So first of all, what is magnetism? We were kind of familiar with these things as kids. Whoops. I bought these on Amazon. They look bigger in the picture, but we know that they kind of push apart when you try and put two norths together, and a south and a north, they pull together. So it's some kind of force. And we can describe them using fields. So in physics, a field is basically just, we can have some point in space with some physical quantity, and we assign a number to it. So every time you look at a weather forecast, you see the numbers on the screen. That's a field. It's telling you what the temperature is in a certain location in space. So magnetism is actually part of a wider phenomenon called electromagnetism. So electricity and magnetism are actually intimately connected. You kind of don't have one without the other. So electric fields, you have some charged particle, electron, and all the fields come out, and these are like monopoles, so they can exist by themselves. But magnets are dipoles, which means they have a north and a south, and their fields go in loops. So electrons or charges, fields emanate out, magnets, fields in loops. So what do you think happens if I cut a magnet in half? Will I get just a north pole by itself and a south pole by itself, or will I get two magnets both with a north and a south pole? So hands up for two magnets with north and south pole. And anyone think you can have a north and a south by itself? Okay. Well, I'll tell you the answer at the end. So the connection to electricity was shown by Hans Christian Ørsted in the 18th century. So you can do this experiment where you basically take a brass rod and you pass an electrical current through it. And if you take a magnetic needle, when you increase the current, you'll see that it's deflected. So basically, when you pass a current through, you have charges moving through it. And when charges move, you have a moving electric field, which creates a magnetic field at right angles to it. And we can use this right-hand rule to tell us which direction this field is in. So along this wire, we use our right hand, point the thumb along the way the electrons are going. We have a magnetic field going like this. That overcomes the magnetic field generated by the Earth, which the compass points along, and we can deflect it. And they're both two sides of the same coin. So instead of moving the electrons to move a magnet, we can move a magnet to move electrons. So as we move the magnet towards this coil of electricity, it generates a current which then lights up the light bulbs. This is how power generation works in all cases, really. So you have some power plant. It's usually, you have something that heats up some water, which generates steam. That steam turns a turbine, and inside that turbine you have some magnet which rotates, and that generates electricity. It's also how microphones work. So inside a microphone, you'll have something that moves. So you have sound, which is a pressure wave, that moves your microphone back and forth inside, which has a little magnet attached to it. That magnet will generate an electrical current, which then can be recorded. And then the opposite case, we can use the electrical current to move a speaker. So we can use electricity and magnetic fields to record sound and generate sound. And this is a motor. So you're basically taking this concept and making it turn it into a circular motion, and that's how we have motors. So every time the motor turns half, you change the direction of the electricity, and it keeps the motor moving round and round and round. And the opposite of that is the generator, as I discussed before, how we produce power. So now we can explain the motor. So the turntable, same concept. You have a little magnet inside the reed head, and as it moves across the grooves in the record, generates an electrical current, which then goes to your speaker, which moves the speaker at the same frequency as those grooves. So light is actually electromagnetic waves as well. So when you have propagating light, you have electric and magnetic fields perpendicular to each other like this. And depending on the frequency, which is, so depending on the frequency, which is basically just the distance between two peaks, we have different wavelengths of light. At the high end, we have things like gamma rays and X-rays, which are high energy and can destroy human tissue. And then on the left side, we have things like radio and microwaves. So like radio waves, because they're long wavelengths, we can send signals across long distances, over hills, and through buildings and stuff. So that's how telecommunications work, basically. So we've also explained not how the headphones work, but how they connect to your mobile phone, because they'll be sending electromagnetic waves between each other. So what about the Earth itself? The Earth's a magnet. Now, you might naively think it's just one big bar magnet, but in fact, there's a solid iron core at the center of the Earth, but around that there's a molten core, and that molten core has convection current, so you have moving molten iron, and that molten iron basically generates magnetic fields. I think I can't remember the guy who first proposed it, but he proposed it to Einstein, and Einstein said, no, your theory's too complicated, because it was lots of little, like, what would you say, very turbulent, but lots of little loops. But all those loops can add up, and that was something that Einstein was wrong about. So now we've explained how the Earth's a magnet, and how magnetic compasses will point along Earth's magnetic field. So far I've just talked about magnetic fields, but what about how this is made? So how do we get magnetism? Because this isn't magnetic, but this is, like, why? So if we look inside this magnet, as I said earlier, if we chop a magnet in half, you get smaller magnets. So the magnets exist there before I chop it in half. So we can imagine the magnet being made up of even smaller magnets, all pointing in the same direction. So here the arrows just represent north and south. So it's just an easier way to draw which way the magnets are facing. So over time, these magnets want to minimize energy. So in physics, things want to be in the lowest state of energy possible. So in a magnet, to do that, it wants to have its internal field at a minimum. So it does that by creating these loops. So now, in this case, all the magnetic field is trying to get out of the magnet. But to stop that from happening, what these are called are domains. They will make these sort of circular trajectories, which then minimizes that energy. But we can apply a magnetic field to realign everything. So then this will become a permanent magnet again. What about if we look even deeper into these domains? So a ferromagnet is when there are the atoms or the magnetic moments that generate the magnetism, they're all pointing in the same direction. So that's what we call ferromagnetism. But we also have ferrimagnetism, which is where you have the neighbors are pointing in different directions, but one of them is slightly stronger. So overall, you do get a net magnetic force. Then we also have antiferromagnetism, where there's no magnetic force because each element that makes up the magnet is pointing in different directions. These are actually quite exciting for some technological applications. I won't discuss today, but they're pretty interesting materials. Oh, it's done two by accident. Okay, so what about the atoms themselves? So we're all happy with the idea of things having mass and charge. But these atoms also, and electrons, have this property called, for this purpose of this talk, because it's a layman audience, tiny magnet. So a proton is a tiny magnet as well, a neutron is a tiny magnet, and an electron is also a tiny magnet. But if you notice, this number is 1,000 times bigger than a proton and a neutron. So why is that? So electrons, we can simplify the picture, whiz around the atom. So this is basically like a loop of current. And as I said earlier, if you have a loop of current, you generate a magnetic field. So this electron's whizzing around, it's generating a strong magnetic field while it orbits the atom, the protons and the neutrons at the center. But we also have this thing called spin angular momentum, which is the electron, shouldn't really say this, but it's spinning on its own axis and generating its own magnetic field. Really, it's an intrinsic property, but it's a nice way to think about it. There's this idea that electrons have spin half, which means it has to rotate around its own axis twice before it gets back to the original position, which is kind of hard to visualize. But one way to do it is if you take your beer in your hand, to get this to go, for me to rotate this twice to get back to the original position, I can do this. Whoa. Oh. I should have, apologies.
Happens every day.
Sorry about that. But that's what spin half means. Okay, so we have electrons, but different elements have different number of electrons around them, and they have different shells. So an atom doesn't just have an orbit of an electron going around like this. That's kind of a simple picture. The electrons can be in these probability functions. So the electron could be within those volumes, right? So as I said earlier, we want to minimize the energy. So if we have one electron and we want to put it into one of these shells, first it'll go into the lowest energy, which is the s orbital. Does anyone want to guess where the next one will go? Actually, I need to tell you something about electrons first. They're really antisocial. They don't like being near each other. They repel each other. So does anyone want to guess where the next electron's going to go in this picture?
P orbital.
Okay, any other guesses?
1s2.
2 p orbitals. Side.
You think here?
Jump to 2.
So this is energy, so increasing energy, and it wants to go in the lowest energy first. So it's going to go,
Splitter.
it's going to go there because this is low energy. It wants to be in the lowest energy, right? Balls roll down hills. Electrons want to sit in the lowest energy. And the reason it has to be in the opposite direction is because of the Pauli exclusion principle, which says that two fermions, which are electrons, have to be in can't occupy the same state at the same time. Or we can also think about it. Our magnets, they want to be like this. They don't want to be like this. If these were strong magnets, which they're not, they'd flip around like this. So we can think of it being like this, right? So next one is here. And what about the... Okay. So we've got 4 different choices. Hands up for blue. Hands up for purple. Hands up for red. Hands up for yellow. Okay, so if we think about our electrons, it's going to go. So electrons, as I said, they're antisocial, so they want to be furthest apart. So this is them both rotating around in this direction. And they want to be far apart, right? So it's not going to be here. So it's going to be in one of these two, right? But this situation is lower energy than this because in this one, the electrons have to come close to each other. Whereas if they stay like this and rotate around the same direction, they are far apart. So that means they have the same orbital angular momentum, which means they both point up. So they're far away from each other and they're both orbiting in the same direction. And then the next one's here. So you can kind of think of it as like when you get on a bus, people tend to go to the first empty seat, the next person goes to the next empty seat. But then once all the seats are filled with one person, you have to sit next to someone. But then you want to sit, you don't tend to look at each other or talk to each other, you kind of look. One looks out the window, one looks the other way. That's kind of how electrons behave in these orbitals. So if we have an unfilled shell, sorry, this is playing up. Okay, so if we have half of the shells are filled, now all our arrows are pointing up, so we have a net magnetic moment. So this means this atom will be very magnetic. But there are lots of elements in the periodic table that don't have full shells or have half full shells. If they're full, you get diamagnetism, so basically no magnetism. If they're paramagnetic, where they have a few that are, you have a few empty spots, they're only magnetic when you apply a magnetic field. What about ferromagnetism, where there is a magnetic field. I'm not applying any magnetic field. These are still magnetic. Unfortunately, this is the part of the talk where I can't give a lay explanation. I've tried to find analogies, but it's to do with quantum mechanic probabilities and exchange interactions, and takes pages and pages of horrible math, which I can't do myself. So, but it's kind of to do with symmetries and energy minimization. Sometimes it costs less energy for all the magnets to point in the same way than if they line up in anti-parallel states. I'm going to skip that. So now we have solid state stuff. So if we look at cassette tape, we have these things called domains, which I mentioned earlier. So the white would be the magnetism's pointing in one direction, and the black is the magnetism pointing in the other direction. And we can encode information as ones and zeros, which can then be read out by a read head. So as the tape goes along like this, our read head will read either a high magnetic field or a low magnetic field, and that's how we can turn that information into sound in a cassette tape. And then this is like an old hard disk drive, which isn't playing.
Sorry,
Oh, that video's not playing for some reason.
oh, you're gonna for videos you have to actually click.
Oh.
And, oh, you can't play it.
Oh, it might be the codec. But basically, it's the same kind of thing as here. Your disk like spins around, and you have, when you apply a high magnetic field, it will switch the magnetism. So the magnetism will switch when you apply a large field. And if you apply a small field, you will read whether it's a 1 or a 0. So that's how we can store information. This has like mechanical moving parts. So if you have an old hard drive, when you turn it on, you can kind of hear it whirring away inside. So to overcome this problem, because that takes a lot of power to make that thing move around, there's this thing called magnetic random access memory. So these lines, we can apply electric current, and then we have these stacks. So we have like, in this case where we have the magnets pointing in the same direction, we'll measure a high a high resistance. But if they're pointing in opposite directions, we measure a low resistance. And this is because electrons are like magnets as well. So if we try and push magnets through this, a lot of them are going to be scattered. Whereas in this case, half of them are this way and half are that way. So a lot more of them can get through without being scattered. Whereas in this case, all the ones that are pointing this way are going to be scattered as they move through. Oops. So in this case, instead of having something moving around, we have these like stacks. And we can apply a current along this line, and then we can either read this one by applying a small current, or if we apply a large current, we can write a 1 or a 0. Is that one going to work? No.
You'll have to scroll.
It's okay. So what have we got left to explain?
Am I right?
Yeah. So, how much time? Okay. So far we've just looked at static magnetic fields. But if we look at ferromagnetic resonance, this is where we have some magnet here, and we apply magnetic field, and that gets all the magnets to point in the same direction. And then right angles to it, we apply another small magnetic field, and what that does is it kicks the magnets so they kind of start processing like a spinning top. And the frequency of that spinning top, when it matches the frequency that we're kicking it with, imagine like pushing a child on a swing. If you push them and then you wait for them to come back, that's the resonance. But if I push like this, but they're over there, I'm wasting energy, right? Pushing when there's no swing there. Or if I push too slowly, I'm wasting energy. But if I push at just the right frequency and wait for them to come back and then push again, all my energy has been transferred into that system, and we can measure that as like a dip in the power in our measurement apparatus. And we can also do, if you've ever heard of Chladni patterns, where you take sand and you put them on top of like a speaker, and then depending on the frequency of the sound generates these different patterns. Same thing happens in magnets. We can see how these things called spin waves. So that's when instead of the whole magnet processing at the same frequency, parts of it process and other parts don't, and you get these cool patterns. So the way MRI works is you have a magnetic field and you have a gradient, so we have stronger field at the top and lower field at the bottom, and that basically allows us to control the frequency of all the atoms in your body. So we apply a huge field and then we kick the atoms and they spin, and depending on how quickly they go back to their resting state tells us what the atoms are, what kind of atoms they are, so if it's a fluid or a fat. And because we've changed the frequency of the top versus the bottom, we can then select a slice along your body, and then we can produce these images. So the only thing left is the maglev train. So these were experiments from Eric Lathwaite in Imperial College in London. And basically, he has this coil, two coils inside of each other, and you basically have magnetic fields that are doing this, which want to push. When he puts a plate on top, it wants to push it out, and then on the outside you have magnetic fields going this way, which want to keep it in. And in a moment we'll see that it levitates.
What is that he has there? Is it a magnet or just a piece of metal?
This is just electrical wires wrapped around some magnetic cores. So when you put wires around a magnet, it increases the strength of the magnetic field. So yeah, this is the first, I think one of the first demonstrations of magnetic levitation.
What year was it?
This was in the 50s, I think, or 60s maybe. And then you can flatten this out. So you basically take this circular structure, you flatten it out, and then that becomes a track. You can then have something which floats on top. I don't think that's how maglev trains actually work today exactly, but this was kind of the prototype. And I think that's everything covered. I don't have time to discuss my research, but
90 seconds.
okay. So as I was saying before, I look at spin waves. So this is kind of a toy model of it. So when you apply a little magnetic field in the middle, you can transmit information along. And my latest thing is like using, so this background, which has been on every slide, is actually the material I work on, which is we basically create these little tiny magnets in these patterns, and we can control how spin waves behave. And maybe I'll end on going back to the monopole question. So in these materials, you can force the magnets to all point inwards, and there you have basically 4 north poles pointing towards each other. So it's not really a monopole, but it behaves the same physics that monopoles, if they existed, would behave as, if that makes sense. But yeah, thanks for listening, and happy to take some questions.
Thank you very much. Yeah, we have some time for a couple of questions. The floor is open.
So I still don't quite understand why some things are magnets and why some things aren't. Like, for example, a wooden table. Does that not have like north and south poles so that like a magnet?
So the atoms that make up carbon, I think. Basically, the atoms that make up carbon, carbon's, let me find the periodic table.
Oh, sorry. Let me just
Oh,
go
back.
back.
I was doing blackout, sorry. Okay. So carbon's here, which means most of the electrons in the shell are almost filled up, so it doesn't have a large magnetic moment. So when you don't apply electric field, it basically isn't magnetic. It has a very small magnetism, but and then the atoms in the structure itself. It also depends on the crystal structure of the material, which I didn't really touch on, but there's a few things at play. But carbon's not a very strong magnet as an atom, and then the crystal structure of it as well means it won't be magnetic on a larger scale.
Does anyone have other questions? Because I have another question.
Oh, wait, let's back there.
So I know that in my electric guitar, the pickup is a magnet, right?
Yeah.
But that's a passive pickup. What's an active pickup then? Is it a magnet that's being powered, or is there like an amplifier behind the magnet? You see what I mean? Like, could you power a magnet? I guess is my question. would that do anything to the?
I'm not sure how active pickups differ. I do know that. No, Nadine's going to laugh at this, but do you know Matt Bellamy from Muse? He has a pickup which generates a magnetic field in it at the frequency of the strings, so that's why he can sustain a note. So he has a magnet inside. So he has special pickups that do that. I'm not sure the difference between an active and a passive pickup exactly.
Right.
But I'll look into that.
Yeah, please.
Thanks
I
for the
just know
question.
they sound gnarly. That's
You mentioned audio tape,
Yeah.
and you said it was digital, like the ones and zeros. Is it the gradients? Like, for example, an audio tape is supposed to represent a sound wave
Yeah.
frequency. Is that frequency purely digital, or is it due to the strength of the magnets on that tape?
I think the tape would have to be a digital, because there are clear domains of up and down within a cassette tape, so I don't think it could detect an analog signal. Because whether magnets don't really tend to continuously change like that. You do get like chiral structures in certain magnets, but they're kind of more exotic materials that tape wouldn't be made from, and I think it is just these domain structures.
And are you able to elaborate on how, for example, a loud sound or a soft sound would be able to be represented? Is that a larger domain of one pole?
I guess it's the same as a CD, right? It's just ones and zeros. So however they encode volume in a CD, I'm not too sure, but I guess it's the same reason. Obviously with like a record, the volume is determined by how far the needle moves. That is a purely analog signal.
But isn't magnetic tape also purely analog? Because it's on a tape head. There's no processing going on. It's going straight into the...
That's true.
I think there were two types.
Yeah, right. There's digital tape. There's, but yeah, I was just wondering.
Yeah, maybe. I think I'm good because I've just used that image is what's burned into my brain. So there probably is analog tape, but I don't know precisely how that works. But yeah, if it's something that could change continuously, then yeah, you could have an analog signal.
Sorry, yeah.
Yeah, I got a question about the magnetic rand part.
Yeah.
Like, I got a few questions. First, like, if it loses, okay, if it loses power, does the information still exist? It's like,
So this system is non-volatile. So if I
oh yeah,
turn all the power off, it'll stay in that state.
oh yeah, but how good is it, like, the information density
So the information density for this is far higher than a traditional one.
for the traditional electron ones?
Yeah. So versus say a mechanical one or an electrical
Why
one.
do you think that is not commercialized?
But it's starting to be commercialized now.
Oh, really? That's awesome.
There are hard disk drives, not disk drives, sorry, HDDs are...
Oh, HDDs are already utilized.
Yeah, or SSDs, solid state drives, are using
SSDs are
similar technology to this.
That is called. Yeah.
But yeah, the problem with this technology, it takes quite a lot of current to like switch these things. So a lot of the research is in getting these things to switch at lower fields and current so that they're more energy efficient.
Alright, thank you.
You had an extra question? Okay.
Can I ask?
Yes, go ahead.
Yeah.
I was wondering if these magnetic domains, can you like see it, like maybe under some kind of microscope? Is it like visible? Because of course we
Yeah,
only
yeah.
see the painted ones.
There's a few techniques that you can do. There's one where you basically, it's like the record player, right? You take a tip with like a laser pointed on the back of it, and that laser then is reflected onto a CCD camera. And basically, as you move it across, it's a magnetic tip, so it'll be deflected by different magnetic structures underneath. And then depending where the laser is moving on the CCD, you can then use computers to rebuild an image of the topology and the magnetic structure. Then there's other ones where you fire X-rays, which will, if it's the magnetism this way, the X-rays get bent that way or that way, and then you can determine whether the domain is pointing up or down or to the left or to the right. So yeah, so we have techniques to measure these things directly. Domains are quite big as well. relatively. Like,
it's
so the
not
domains
like-
are on the size of microns. So once you get small enough, you can't form domains anymore. So these structures here are a few hundred nanometers, and you don't get domains forming inside them because they're too small.
All right. I think that's perfectly the right time. So,
Awesome.
Everybody know the humor round. Another round of applause. To the Dion. Thank you very much. We'll take about